And Chris has over 25 years of industrial and research experience in application of in-vehicle networking technologies like CAN, CAN-FD, J9039, NME 2000 LIN, FlexRay, as well as automotive controls such as braking, steering, and powertrain control. Chris is a PhD from University of Warwick, and his regular participation in vehicle networking standardization as seen CIA, NME 2000, and ISO. And Chris is a co-founder and director of Warwick Controls Technologies, a company specializing in providing diagnostic tools, training, expertise for in-vehicle control, networking, and analyzing. So Chris, please take the screen and make your presentation.
Okay, thank you, Kent. Good afternoon, everyone. So I'm going to talk to you today about the paper's entitled benchmarking of CAN systems using the physical layer and the car, truck, and marine case studies. So really what we're talking about today is we defined what we call a CAN electrical signature methodology, which can be used in situations in which you might have to work with a CAN system, but you don't have full information on this system. So these could be things such as in the automotive environment, you might want to reverse engineer parts of the CAN bus so you can carry out benchmarking exercises. Or there might be a vehicle that needs maybe retrofitting of some kind of CAN bus system, and make some kind of new prototype for that. There may be telematic systems which you want to be able to get information from the vehicle for fleet management purposes, and quite often some of the information available is not as full as perhaps might be required by the fleet manager. There's also situations where you not fit additional systems to the vehicle, such as for disabled drivers. And then finally, you might want to be able to work out if there's a rogue device on the system. And so what we're going to go through in the next half an hour is really this kind of methodology that we've developed based on looking at the CAN electrical signature, and how we've used this in a number of different applications over the last few years. So it's really sort of this year's update of the state of the work we've carried out. So what is a CAN electrical signature? In our case, it could mean lots of different things depending on how you define it, and effectively the electrical properties of the CAN bus signal will be influenced by a number of things, such as the components within the ECU, the position of the network node within inside the CAN bus, the length of the CAN bus, the type of the wiring that is used within inside the CAN bus, and age of components, the use case or use environments. It could be things like if you're working in an environment with high vibrations. So there's lots of different scenarios that affect the CAN bus electrical signature. And what we get onto now is how we've defined what we're going to use as our CAN bus electrical signature for using these kind of reverse engineering and benchmarking type applications. So you can see on the screen here, we've got an overview of a CAN frame, or sort of a simplified overview of the CAN frame in sort of a block form. And I think most people will be very familiar with this kind of outlook. And you've got things such as the identifier, which can be 11 or 29 bits, or the data field, which can be up to 8 bytes long, and then you've got the CRC acknowledgement. Well, what we need to use for our application is to determine parts of the frame which are unique to a ECU that is transmitting information. So because we want to use the parts that are unique, what we do in our process here is we isolate the data field, because the arbitration field or the CAN identifier could be influenced by other nodes on the network due to the arbitration process for access to the network. Also, the acknowledgement field will be filled in by one or more devices that have actually received the CAN frame successfully. So therefore, we actually need to just look at the data field of the CAN signal. So we've got a picture here of the CAN bus arbitration process, where there are three devices taking access or trying to take access to the network. And this kind of shows why we should not use the CAN identifier within the electrical signature. You can see we've got three different devices here: node A, node B, node C. And at different times, they're all trying to get access to the network. And depending on the identifier, then the ones with the lowest priority actually lose access to the network. You can see this happens such that the one with the highest priority gets through to the network. And this is how it manifests itself in this picture here, in an oscilloscope trace taken from a CAN, a simple CAN frame. So you can see on the side here, we've got the actual voltage in millivolts, and then we've got sort of areas of the CAN bus signal. We've got the arbitration field, the data field, and the acknowledgement bit. Now, if you can see on the left-hand side, there's probably maybe a bit or two during the arbitration field of the starter frame, whereby there's more than one device trying to transmit at the same time. And so because of this, you end up with a higher peak in the voltage there. And this is one of the reasons why you could not actually use that part of the CAN frame. Also, if you look at on the right-hand side, you can see the acknowledgement. And because lots of different devices are trying to transmit at the same time, you should also ignore that part. So the part we use here, you can see basically in the data field, so the steady part here in the middle of the CAN frame, it's a nice stable voltage, so that we can actually use this, effectively take sort of like an average level, and we can use this as an identification of what our CAN electrical signal should be. And then this picture here gives an example of how it differs between two different networks. This is taken from a passenger car, and you can see on the left-hand side, we've got one particular ECU. I think basically one is an engine and one is the braking ECU. I cannot remember which one's which exactly, but that doesn't matter for this particular purpose. But you can see the one on the left-hand side, the CAN high level, which is shown in the blue, has a sort of average level for the dominant part of the CAN frame, sitting around the 3,500 millivolt level. And then the dominant part of the CAN low signal, shown in the sort of orangey brown there, is around the 1,500, or slightly above the 1,500 millivolts level. If you look on the right-hand side, you can see that this differs slightly for the different ECU. So in this case, the dominant part for the CAN high level, shown in the blue, is below the 3,500 millivolt level. And again, with the CAN low part, this is below the 1,500 millivolt level. So these very small differences actually do give away something about the actual ECU that's transmitting the actual signal. So we've generated a kind of semi-automated process whereby we use off-the-shelf tools such as the CAN bus analyzer with a PC oscilloscope connected, whereby we can basically record one example of each different CAN message that is transmitted on a network within a certain time frame. So you can set up the time frame. I think in this example we've sampled data within a 10-second window. So what you do, you can see on here, we've taken a copy of each CAN frame that's transmitted on the network, and then you can see at the bottom you've got the the electrical trace of the actual CAN signal showing CAN high, CAN low. We've even got the differential shown in the green part. So then what we do, we can save this as a group of Excel spreadsheets, which are saved with this information you can see on the screen here. So you've got the identifier, and then you've got individual samples, maybe down in sort of maybe 100 nanoseconds or sample level. And then you've got a group of CAN high and CAN low voltages. So basically, across a whole frame, you might, it depends on the bit rate, of course, but you might have a few thousand samples for a complete CAN message there. And then we've got a process whereby we then manipulate this data. So remember from before, I was saying we need to look at the dominant part of the data field. So there's a process, as you can see on the slide here. So the first part is that we log an example of each CAN identifier that we find on the network. And then we isolate the data field. So this kind of process, we've done this just using VBA scripts inside the Microsoft Excel. So that's just something very simple, but you could use other ways of doing this. But so what we've done, we've pulled out the data field part of the CAN frame. So we're removing the CAN identifier and removing the acknowledgement field. And once we've got the data field, we then split this into the portions which are dominant or the portions that are recessive. And then effectively at that point, we have a group of samples, and of course there is going to be some noise in the signal. So we calculate an average, and depending on the type of noise you see in the network, sometimes you can use a mean, or sometimes you can use the modal average. It's worth trying both to see which ones give you the most sort of interesting results. And then the final part is, and this is where it comes in very useful using Excel, is you can make a plot of this in Microsoft Excel. So basically you get a cluster plot, and where the groupings of the actual clusters are basically the groupings of the messages sent by one single ECU. And this gives just an example with the previous example of the passenger car, which I showed a few slides ago. So you can see on the x-axis, which of course not labeled, but it's hopefully you can see that on the screen there. But it's basically the CAN high voltage in millivolts, and on the y-axis it's the CAN low voltage in millivolts. And so effectively, each CAN message signature is basically the average of the data field dominant signals of each message on the CAN bus. So you can see we group these together. Because we have the CAN specification of this particular vehicle, we were able to confirm this. So you can see there on the left-hand side, you've got a reasonable cluster with about maybe 8 messages for the vehicle stability system. And then next along, you've got maybe about 10 messages for the instrument cluster. And then going out maybe 8 messages for the engine. And then there's finally on the right, you've got the supplementary restraint system showing 3 messages in a cluster. And so this works quite nicely. And then we sort of got an example here of how we've used this in a reverse engineering process. So the previous diagram showed that how it clusters nicely on a vehicle we've got known CAN specification information on. However, the interesting part of this application is that you can put it onto situations where you do not have full information of the CAN specification. So therefore, it's good you can use something which is known about the vehicle already. So what we've done in the past if you're trying to identify which messages are sent by which particular control units, it's good to use known information. And with a passenger car application, the known information is actually the diagnostic messages, because they are specified within various protocols such as ISO 15765. So, for example, when you make a request, the sort of request that could be carried out by typical diagnostic tools, the engine responds on 7E8, and it's typical that gearbox ECU will respond on 7E9. And you can use this information to, basically to put, work out a cluster of the known information. You can compare this to the unknown real-time messages which you find on the CAN bus. So you have a process whereby you make the diagnostic requests, you then log the diagnostic responses, and then you carry out the generation of the CAN electrical signature, and then you can actually examine the clusters and see what compares to what. So again, we've got a different vehicle this time, and that's one with a fairly simple control system. But you can see on the left-hand side, we've got the diagnostic responses. Basically, so that the request was made using a diagnostic tool, and the response came back, and we measured the actual electrical information. And we knew that, for example, 728 in this case was the instrument cluster, 7E8 was the engine, 738 was steering, and 768 was the brake controller. And then you can sort of compare on the right-hand side, whereby you've got, a cluster of CAN electrical signatures for the instrument cluster, the engine, steering, and brake control. That's a simple powertrain network. Then we've got one on a body control system from the same vehicle. This one had a very simple diagnostic setup. It only had 2 ECUs respond to diagnostics. You can see we've got 7.3F, which clusters quite nicely with 2 IDs on the top left part of the right-hand cluster plot. And then you can see with 7.2E, you can see that there's another cluster there, but a bit more spread out. Now, this does not give a definitive answer. You should only use this kind of approach to give you this information and part of the analysis and the breakdown of a CAN network. It could be within that cluster on the right-hand side there that they're not all from the same ECU. It could be that, for example, only one ECU is responding to a diagnostic. It might be others don't respond to diagnostics. So there could be maybe more in one cluster there. But it could be one ECU as well, so it's just something to bear in mind. We've got a more complex example here from a British SUV powertrain network. And you can see that there's certain patterns there that's a little bit more complicated. But again, if you dig down deep into how the diagnostic IDs actually match with the different real-time identifiers, you can use it to help you match which ECUs transmit which information. There's another interesting one from a van powertrain network. So just like the delivery van, you can see there's actually sort of fewer clusters of information for the diagnostics compared to the clusters on the real-time network. So what this is showing here is that there could be a problem down to, it could be measurement error, it could be not all ECUs are having diagnostic functionality. It could also be that some further collections need to take place to be able to dig down deeper in what's going on. It could also be that the method is not working so well on this particular network because of the particular characteristics of the actual the actual CAN bus electrical signatures. We're getting to rogue ECU detection in the approach, and we've seen a number of things whereby this has been quite useful in projects we've worked on. So there could be CAN bus cybersecurity in general. There could be a reason you might want to do this. I mean, for example, when you're developing a vehicle and you're working on a prototype vehicle or a prototype CAN system, and then down to the incompetence of one of the partners in the project, they might configure an ECU incorrectly and send the wrong CAN identifiers. So this will help you identify that not all is correct on the system. There's another problem which we've worked on with in the trucking industry, which is a particular problem whereby a lot of cheap devices are available, which are just maybe a few tens of euros, and they will pretend to be the AdBlue system. And looking at this kind of clustering can help you sort of understand if a particular control has been overtaken or manipulated or replaced. You get a similar problem on trucks with tachographs as well, whereby the actual readings on a tachograph are changed to for not so honest reasons. People put systems onto CAN buses to enhance the performance, and finally, potentially there could be systems put onto a CAN bus to make the actual system become dangerous. So showing another cluster plot here then. So this time we've got CAN low on the bottom for the x-axis. We've got CAN high on the top, on the right-hand side for the y-axis. We're showing different. This is a J19. It's actually a bit of a mixed J1939 NME 8000 example, which is a bit of a curious one. This is a case where you've got this 29-bit CAN protocol. They're both very related protocols. And in this case, they should have each transmitting device should have a unique source address, and there's the possibility whereby the source address can be sort of plug and play and be configured on the fly on the actual system, or it can be hard coded. And this particular system, we had two systems which were transmitting on source address 09, which created some interesting kind of side effects. So what we did, we produced the cluster plots, and we realized that one of the devices which was supposed to take part in the full J1939 and the 80,000 address claim process was not, and was basically effectively sitting permanently and squatting on the 09 source address. And you can see circled in the red with the yellow highlights, there's basically two distinct network devices there which using the same source address, and only one of those is using it correctly. And we've got another similar one again here. In this case, we're showing, this is actually a full J1939 example, which is just showing the source addresses in hexadecimal. So we remove the rest of the CAN frame. It's showing the source addresses and how they are actually clustering nicely. But again, we've got two devices which are trying to use the source address 30, which again, is illegal by the protocol. So we've given an overview of what we would call our CAN message electrical signature. And so we use this to effectively, reverse engineer the system and benchmark the system. We've done this by using our CAN bus electrical signature, which basically isolates the data field alone. And there's now, a number of applications we found this is quite useful. From the experience of looking at this in the last few years, I would not say you can say it's a definitive approach that will give you 100% accurate approach all of the time. And you would always have to use your own kind of grey matter and use your brain on how to actually interpret the results. However, it is a very useful decision support tool. And we're working on some hardware to sort of semi-automate this, well, to automate this process more. We've already got a semi-automation in process. We're looking to see if we can automate this further. And then there's other parts of the CAN frame that can also be used. For example, you can use bit timing differences. So these are other things that can be looked at as well. So by using a lot of these different approaches together, you might be able to get a much more definitive answer. And we have not looked at this yet, but potentially this could be applied to other networks which use, twisted pair type wiring and differential signaling, such as CAN-FD and CAN-XL and FlexRay, Ethernet type applications. I mean, the key point is we're looking for that kind of, very small voltage difference in the unique parts of the message frame, which are unique to that particular ECU. And that's the end of my presentation. Thank you for listening, and there are my contact details if anyone wants to contact us for any more information.